All right, let's dive into a really cool puzzle at the heart of how our computers work: inter-process communication. We're going to explore how all the different programs on your machine, which are built to be totally separate, somehow manage to talk to each other and get things done.
I mean, think about it. Right now, you've probably got a web browser running, maybe some music playing, your code editor. Each one is its own little world, a separate process. So how in the world do they coordinate? When you copy some text from a web page and paste it into your notes, how does that information jump across the heavily guarded wall from one program to the other?
Now, this isolation thing, it's not a bug, it's a feature, a super important security feature. Your operating system intentionally puts every process into its own little sandbox with its own private memory. This is great because it means a bug in one app can't bring down your entire system. But it also creates this fascinating challenge. If every program is in solitary confinement, how do they team up for complex tasks? They need a way to communicate. And they have some really good reasons to talk. The most obvious one is sharing information, like our copy-paste example. But it's also about speed. You can crush a massive task by breaking it into smaller pieces and having different processes work on them all at once. It also helps developers build better software using smaller modular programs that work together. And, at the end of the day, it's just plain convenient for us. We want our apps to play nice together. So how do we solve this isolation problem? Well, it pretty much boils down to two main approaches. You can think of it like this. You either give the programs a shared whiteboard they can all write on, or you set up a super reliable postal service to carry messages between them. Let's look at the shared whiteboard first. In the tech world, we call this shared memory. The idea is actually pretty straightforward. The operating system steps in just once to set up a special area of memory that two or more programs are allowed to access. And here's the magic part. After that initial setup, the OS just gets out of the way. The programs can read and write to this shared space directly as fast as they want with no middleman. As you can guess, this is incredibly fast.
The other option is our postal service, which we call message passing. In this model, there's no shared space at all. If one program wants to send something to another, it bundles it up into a message and hands it off to the operating system. The OS then acts like a postman, delivering that packet of data to the other program's mailbox. The key difference here is that the OS is involved in every single exchange.
And this comparison table really gets to the heart of the matter. Shared memory is blazing fast because there's no OS slowing things down, but that speed comes with a big catch. You, the programmer, have to make sure the processes don't write over each other's data at the same time. You have to manage all that synchronization yourself. Message passing, on the other hand, is slower because the OS is always in the middle. But for that performance cost, you get simplicity and safety. The OS takes care of all the tricky synchronization stuff for you. Okay, so those are the big ideas, the high-level models, but how does a programmer actually make this happen? Let's pop the hood and look at the actual toolkit developers use. So the simplest and most classic example of this is the pipe. It's basically a one-way street for data. One process shoves data into one end, and another process pulls it out from the other end. And hey, if you've ever used a command line, you've used pipes. When you type something like ls/grep.txt, that vertical bar is a pipe. You're literally telling the system to pipe the output of the ls command directly into the grep command as its input. And here's a peek at how that works. A main process, let's call it the parent, asks the OS to create a pipe. Then it uses a special command called fork to create a clone of itself, a child process. Now you've got two related processes that are connected by this pipe. From there, they just need to agree on who's writing and who's reading. Maybe the child does the talking and the parent does the listening. What's really important to get is that these abstract ideas are brought to life by real system calls. These are the official requests your program makes to the operating system's kernel. As you can see, whether you're coding on Windows or Unix system like Linux or Mac OS, there are specific magic words or functions that you call to create a pipe or to get a chunk of shared memory. These are the actual tools of the trade. Okay, so we've covered the concepts and the tools, which brings us to the big question for any developer working on this stuff. Which one should you choose? And honestly, it all comes back to that fundamental trade-off we've been talking about. It's a choice. Are you building an application where every single nanosecond counts and you're confident you can handle the tricky business of synchronization yourself? Then the shared whiteboard is your best bet. But if you value safety, simplicity, and letting the OS handle the complicated details, then you'll go with the postal service of message passing. And I'll leave you with this final thought to chew on. Everything we've talked about so far assumes the programs are on the same computer. But what happens when they're on different machines, spread out across the network? They can't physically share a whiteboard anymore, right? So they have to use the postal service. Does that mean message passing has basically won in the modern world? Or are there clever ways to create the illusion of a shared whiteboard, even across a network? And that's where things start to get really, really interesting. Thanks for joining me.